Hi everyone, I'm Abhineet, and today we will be reviewing this paper, Darwin, Scale in Stream Processing by Lawrence Benson and Tillman Ribble. And so this paper basically talks about current state of stream processing engine. So there are two types of stream processing engine. One is scale-up systems and one is scale-out. So scale-up system basically offer optimization for higher hardware resource utilization on a single server, and scale-out systems rely on cluster of servers to scale out processing. So they do not do much of hardware resource optimization. Uh, but instead, scale-out systems offer more number of features such as support recoverable larger than memory state with persistent or distributed state management, which is not there in scale-up systems. Some example of scale-out systems are Apache Flink, Spark Streaming, Hazelcast, and scale-up systems. Some of the examples are Brisk Stream, Sabre, and Grizzly. So paper mentions current challenges with stream processing engines. So some of the challenges are that one is resource inefficiency. So as we saw earlier, that scale-up systems, they use some of the techniques for higher hardware resource utilization, such as query compilation, NUMA awareness, lock-free data sharing, and GPU co-processing. So paper finds out that except for NUMA awareness, none of these techniques are exclusive just for the large servers, but they are also applicable for optimization in commodity machines. So in a way, so scale out systems can also use those techniques to use more hardware resource more efficiently. Second is state management. So scale out systems use a general purpose key value store to store state, such as Flink uses RocksDB. But these general purpose key value stores are not optimized for stream processing specific state access pattern. So they have done some benchmarking to show that how if we use a stream specific state access pattern, how much improvement that can make for this slower storage media. So, and the next next challenge is overall system optimization. So a lot of system optimizations which have been done through years in database, so that they can utilize the hardware resources more efficiently, have not been ported to the stream processing engines. And paper proposes that we can start doing that because the operators in a stream processing engine are very similar or comparable to the SQL operators. And also many of the currently stream processing engines are written in JVM based languages such as Scala or Java. So they have some GC collection overhead as well. So to summarize, paper lists out what all are the opportunities in stream processing engine where we can improve for a higher resource resource utilization efficiency. So one technique is query compilation can be used for And this will help in hardware conscious optimization, and push-based execution model can be used. Then in network communication, because network can be a bottleneck as well. So to improve bandwidth utilization by can be done by late merging to reduce the data shuffling, and user space networking can be used to reduce TCP IP. And then cross-server communication performance improvement can be done by using high bandwidth InfiniBand and RDMA connections. The next paper talks about opportunities for state management. So paper compares actually three types of storage systems. One is the classical byte-based key value store, ROXDB, which is used by Flink. Then second is in-memory state management, used by which is Intel's TBB concurrent hash map. And third is Viper, which is modern storage aware key value store. And it is based on a hybrid DRAM persistent memory index and log structure. So they have compared these three systems and come up with these two benchmark. So the first one, if you see here, they compare the insert and get operations. So here Viper gives the most optimal performance in insert. So Viper stores, because Viper stores record directly in the persistent memory log without intermediate buffering to DRAM. And to leverage the higher random access performance of DRAM compared to persistent memory for index updates, its index is located in DRAM. So this hybrid design actually achieves 4x higher insert rates than persistent memory only stores. And here as well, if you see, but in this one, forget TBB concurrent hash map gives like much optimal performance. And for checkpoint and recovery benchmarking, what they have done is they have stored 200 million 50 byte records, that is 10 GB raw data, in 3 different storage instances. And they again use TBB concurrent hash map, Viper, and ROXDB. And for TBB, how they have done checkpointing is they are serializing the record as byte array and storing in SSD. And so in this, if you see, the ROXDB and Viper are very much more efficient in checkpointing as compared to TBB, because ROXDB only flushes its volatile write buffer, and Viper only persists metadata. And in recovery as well, ROXDB performs best as it reads only metadata and immediately accepts the request. And Viper must recover first its volatile index, which depends on the number of entries. And TBB gets all the data from storage and then recreates its memory state, which takes significantly longer time. So that is why worst performance here is for the TBB concurrent hash map. And this actually, as I mentioned earlier, that here paper tries to compare, actually add this buffering, just to show that how stream specific access pattern can improve performance for slow storage media. So here these are two benchmarks. So first one, they have used like multiple threads are sharing same store. And in this one, like each thread is like writing or in fact reading from different store. So if we see here that as the number of records per block increases, the performance of RocksDB improves quite a lot. And actually, this happens because when using RocksDB backend, the operator gets the current value, deserializes it, appends a new value, and then again serializes the updated list back to its byte representation. But if we if for a windowing operation, some buffering is used, then that update for each new entry reduces. So that is why this improvement is in performance is noted here. Also, paper mentions some more optimization can be done by using CPU-aware optimization techniques. So finally, after studying all the shortcomings and the techniques which can be used to overcome them, paper proposes a new system, which is Darwin. So Darwin has in Darwin they have actually used all the techniques for hardware utilizations, which they said that is by compilation, query compilation, whatever higher resource utilization they can achieve. They have tried to implement that, but currently they have not added any optimization for network aware data transfer to achieve higher more efficient multi-server processing or efficient checkpointing and recovery mechanism. So yeah, so we will see that how query compilation technique has helped them achieve higher hardware resource utilization and better performance. So below are the components which Darwin has. So first one is data pipeline. So data pipeline gives a query API to the user so that they can define their data pipeline. Just to give some glimpse into that. So this is code which I have taken from Flink's document. So if your code is something like if your data pipeline is reading from orders table is filtering country as France, and then group by it's doing group by on country ID CNAME, and then doing select country ID CNAME and summing up the revenue. So this can be defined as as a query as well, and its capabilities there in Flink. So similar thing I think they are trying to do here in data pipeline, that a user can easily define a data pipeline as query with some extra operators which are not there in databases. And then after a data pipeline is defined, the Darwin comes up with a query plan. And then once query plan is there, so if you see here, some of the relational algebra operators like select, source, select, then window, then group by, and then projection, and then finally sync. So once query plan is there, then it translates it into operator graph, which is the physical operations which will be done. So here they have used tumbling window aggregation So tumbling window aggregation basically means that the windows are basically independent of each other. So they break this window into three operators: tumbling assigner, tumbling trigger, and summing operation. So once operation graph is achieved, then the query generator takes the graph and then creates a C++ code out of it. And then here the query generator takes the operator graph, and this is the C++ string representation of the actual query. And then query compiler comes into the picture. So query compiler compiles the query code by using underlying hardware details. As the compiler runs independently of Darwin, user can specify a different compiler than that was used to compile Darwin here. And finally, query execution. So query execution, sorry. So depending on the generated pipeline and specified parallelism, multiple sources, sink and operator instances are created in query execution. So if in query execution, if it finds, and Darwin finds out that if pipeline has low utilization, then it merge the nodes are merged to free resources, and if pipelines are creating back pressure, then Darwin splits them to keep up with data rate. And okay, some performance benchmarking this paper mentions. So for performance benchmarking, this is the setup they have done, that a 60-second tumbling window sum aggregation on 32-byte records with 15,000 unique keys. So if we see here, two benchmarking has been done. So one is for in-memory, they have compared with Grizzly, which is another scale-up system as mentioned earlier. And so for in-memory, both Darwin and Grizzly show same throughput, similar performance. But paper mentions that the optimizations which have been done by Grizzly to achieve this efficiency are basically independent of their architecture. So I think those optimizations can be employed here or in other SPEs as well. And then for persistent memory, they have compared Darwin and Flink. So Darwin here uses Viper for persistent memory, and Flink, as usual, uses the RocksDB. So here there is clear difference between performance of Darwin and Flink because of Viper, which is, as mentioned earlier, it has index in it is based on hybrid DRAM persistent memory index and log structure. Yeah, so this was my presentation on this paper. Thank you.